Hi, this question paper is for the IBDP Maths exam from Analysis and Approach Curriculum, higher level. This is paper 3, and this paper is from November 2024. Let's solve this paper. The first question asks, this question asks you to investigate models for the population of trout in a lake. It talks about population of trout. So at the start of a year, a lake is estimated to contain 6,000 trout. The owner estimates that the number of trout will increase by 10% per year. At the end of each year, he proposes to remove 500 trouts to prevent overpopulation. So each year, the population will grow by 10% of the fish, but 500 of them will be taken out at the end of each year. So what would be the net relation after each year passes by? Therefore, the relation between Tn, the predicted number of trout at the start of year n, and Tn plus 1, the same at the start of year n plus 1, is given by this relation Tn plus 1 equals 1.1 Tn minus 500. So 1.1 comes this factor because of the 10% increase on the previous year's population. So here, just for understanding, 10% is equivalent to 0.1. So 10% increase is equivalent to multiplying by 1.1. And of course, at the end, you take out 500 trout fish from the lake. So this relation is called the relationship like this, where you express Tn plus 1 in terms of Tn. This is called recurrence relation. So this is the relation that will be used for first few parts. So one example, if you put n equals 1, the predicted number of trout in the second year can be expressed by the predicted number of trout in the first year. If we put n equals 1, we will get T2 equals T1 multiplied by 1.1 minus 500. Now, T1 is 6,000, that is the estimation for the first year's population. Multiplied by 1.1 gives you 6,600 minus 500 equals 6,100. The first answer is actually to verify T2 equals 6,100 using this formula. In fact, so this is part A. Putting n equals 1 in recurrence relation, you can get the answer. The next two parts as well asks to find T3 and T4, populations of the third year and the fourth year. So T3 we can find in terms of T2 using this recurrence relation. So T2 will tell us what would be T3. And once we find T3, T3 will in turn tell us what would be T4 using this same recurrence relation that is given. It's pretty easy. T3 would be 1.1. We know 6,100 is T2 minus 500. And if you evaluate this, you would get 6210. T4 is 1.1 times P3, which is 6210 minus 500. So this one, I'll have to add 621 to 6210. So 6831 minus 500. This is 6331, and that would be the answer. So this is part one, part two. So we found out T2, T3, T4 using the recurrence relation. That was the first A and B part of the question. Pretty easy. Moving on, it says it is also known that Tn equals 6001.1 n to the power minus 1 minus this term 500 times within bracket 1.1 to the power n minus 1 minus 1 divided by 1.1 minus 1. So this expression is not a recurrence relation, rather this is a closed form expression in the sense that En is expressed in terms of n and some constant parameters, so that for any generic n, you can readily find out what is the value of Tn, or in other words, the population of droughts as a function of the year. Here, you don't need to know the previous year's population like before, where in the recurrence relation, to use the recurrence relation, you had to know the previous year's population in order to find the next year's population. In this case, you don't have to know. This is a closed form expression. So the first part is so that Tn equals this expression. So from here to here, there would be some simplification procedure. So to start with, let's observe that the first term in the given equation that we start with, or the equation that is known, that is simplified to start with. The second term is what we can start simplifying with. So let's try to do that first. 500 times 1.1. So let's observe that the denominator here is 0.1. So when you divide 500 by 0.1, there is an extra factor of 10 that gets multiplied by with 500 to give you 5,000. So we end up getting 5,000, 1.1 to the power n minus 1, minus 1. So now Tn becomes 1,000. That is the first term, minus this part. So we observe that the coefficients of 1.1 to the power n minus 1, we can collect together, and 6,000 minus 5,000, that becomes 1,000. Like given in the final expression that you have to prove, plus 5,000. That is this term multiplied by this term, minus minus become plus. So finally you have 1,000, 1.1 to the power n minus 1, plus 5,000. Science proved. The last part in this page asks for hence or otherwise find T6. Give your answer to the nearest whole number. So you have to find T6. Well, you can just put T6 like n equals 6 in this expression that we just found out, or it is given here. So let's put n equals 6. And T6 would be 1,000, 1.1 to the power 5, because it is n minus 1, plus 5,000. So let's see how much this is. You can use the calculator. So it is 1,000 into 1.1 to the power 5 plus 8,000. This is 6610.51. So the nearest whole number is 6611. So I'll write that. This is 6611. As long as you like reduce it to the nearest whole number. So that's the answer. So the question one continues here. So from the previous part, the owner decides that the trout population would increase too quickly if he only takes out 500 each year. If he takes out from the lake 500 each year, the population would increase too quickly and it would overpopulate. So now he proposes instead to remove 750 trout at the end of each year. So the relationship now would be modified to, here we call it dn plus 1 instead of dn plus 1. So same 10% increase. Instead of 500, you have to subtract 750. And the initial population is, of course, the same for this model. And like before, in the later part we saw, the closed form expression is also given here. So let's just write all in one go. The closed form like expression is negative 1500 times d1. This is the exponential growth part plus 7,500. So the first question in this scenario asks that show that dn plus 1 minus dn equals this quantity. So how to solve this problem is in this closed form. So there are like in this closed form expression we can use. That is the best way to solve this. Or we can combine the recurrence relation that we have and the closed form equation together. So let's do the latter part because the first way is very easy. It's a little bit tedious though, but either way it's fine. So dn plus 1 minus dn. From the recurrence relation, we can first write dn plus 1 as 1.1 dn minus 750 minus dn. So if we collect the coefficients of dn, we get 1.1 minus 1. So this becomes 0.1 times dn minus 750. Now, this 0.1 times dn, here we can substitute the closed form expression of dn. So that is negative 1500, 1.1 and minus 1, 7,500. So let us observe, this is just multiplied by 0.1. The thing is a square bracket. So the first term would be negative 150 instead of 1500 multiplied by 1.1 to the power n minus 1. The second term would be plus 750 minus 750, which will cancel each other. And you end up getting the right-hand side of the one we have to prove. And the second part is asks that use the result in the first part to deduce that the predicted number of trout at the start of any year will be greater than the predicted number at the start of the next year. So at the start of any year, let us say, so naturally we can write dn as the nth year's population at the start of nth year. And the predicted number in the next year would be dn plus 1. And it asks to deduce that dn would be greater than dn plus 1. So how do you show that? Well, we saw in the previous part that dn plus 1 minus dn is negative number, negative 150, 1.1 to the power n minus 1. So here you have to argue that 1.1 is a positive number and any exponent of a positive number is positive. So 1.1 to the power n minus 1 is positive. And hence dn plus 1 minus dn, since it comes with a negative sign in front, this is a negative number, which implies that dn is greater than dn plus 1. So at every year, the population actually decreases. And the next part asks exactly that, or approaches exactly that point, that determine the first year during which there will be no trout remaining in the lake. If each year the population keeps decreasing, then there will be some point that the lake will be out of trout fish. So the question is determine the first year during which there will be no trout remaining in the lake. So let's think about how we can solve this problem. So we are basically looking for that dn where there is still some trout fish, but dn plus 1 when we do not have any trout fish. So dn is greater than 0 and dn plus 1 is less than or equal to 0. Where n greater than 1, some integer. So in this case, there exists a number k which lies between n and n plus 1, such that the closed form expression of dn, if we replace n by k, that is we write 1500, negative 1500 times 1.1 to the power k minus 1 plus 7500, this will be 0. Why? Because dn is greater than 0 and it decreases to less than or equal to 0 at dn plus 1. So there must be a crossing point because dn decreases monotonically in between n and n plus 1. So symbolically, we represent that year as or like that time at by k. And if we can find k, since these are two consecutive integers, n and n plus 1, if we find k, we'll be able to find n and n plus 1, and we can decide that which year the trout fish will be, or like all the trout fish will be gone, or dn will become 0 or less than 0. So this is an equation to solve. So we just rearrange this equation by taking one term to the other side. Observe that 15 is a factor of 75. In fact, 15 into 5 equals 75. So we have 1.1 to the power k minus 1 equals 5. We can take logarithmic on both sides to have k minus 1 log 1.1. Let me just write it. Sorry. So let me just write it in the next line. K minus 1 log 1.1 equals log 5. So here it does not matter what the base of the logarithm is, as long as the base are same. So if we do not specify the base, but we assume that the base is same for both sides log. And we have then k equals 1 plus log 5 by log 1.1. Now we have to use calculator to find what this value is. So let's go back to the calculator. So this comes out to be 17.9. So this is approximately 17.9. And so K is 17.9 and K lies between n and n plus 1, or 17.9 lies between 18 less than equal to 18 greater than equal to 17. So D17 would be greater than 0. D18 would be less than 0. Actually, what is going to happen in reality though, D of 18 would be actually equal to 0, not less than 0, because when the uh, owner is going to take out 750 trout fish, you observe that there is no longer 750 trout fish left. Less than 750 trout fish is left. So you just take out all of them and the lake will be free of, like the lake will have no trout fish left at all. So D18 would actually be 0. So the answer would be determine the first year. So at the 18th year, there will be no trout fish. All right. So first we had a situation where the overpopulation prevailed, that the owner had to increase the number of trouts that he has to remove every year. So if we go back, first he found out that the population would increase too quickly. So he decided to remove 750 trouts. Now he finds out that his lake is out of trout fish by 10th year, as we found out. So we have to optimize, like the lake owner now considers a more general approach where the trout fish will be removed at end of each year. So, and we need to find D such that the trout fish remains same, the number of trout fishes. So this is again the closed form equation. If you remove D fishes each year, so at the start of the nth year, the predicted number of trout will be Cn 6000, 1.1 to the power n minus 1 minus 10d into this value. So find the value of d such that the predicted number of trout at the start of each year is constant. So how do we solve this problem? Cn to remain constant as a function of n. So C1 is equal to 6000. That's the initial population. What we are saying is, what should D be such that C2 is same as C1, C3 is same as C1, C4 is same as C1, and so on. Basically, the trout population has to remain constant. So if we can prove that for any n, for all n, which is greater than 1, Cn plus 1 is equal to Cn, then, so if this is true, then Cn will remain constant. So this is the condition we have to sort of put here and see what condition we get in terms of D. So Cn is 6,000, 1.1 to the power n plus 1 minus 1 minus 10D. Within bracket we have 1.1 n plus 1 minus 1 minus 1 equals Cn, which is 6,000, 1.1 n minus 1. So first we observe that this term that gets from multiplication of negative 10D with negative 1, negative 10D, negative 1, they will give the same term on both sides. So they will cancel each other. What we can collect is the terms containing 6,000 and the terms containing 10D on each side. So if we collect the 6,000 terms multiplying 6,000 is we have on the left side 1.1 to the power n minus 1.1 to the power n minus 1 from the right side. This comes with a minus sign. On the other hand, here 10D with a negative sign with 1.1 to the power n factor will move to the other side. We get 10 to 10D 1.1 to the power n minus 1.1 to the power n minus 1. So this is actually the same factor. The factor in the bracket is same on both sides. So it must be that 6,000 equal to 10D and D equals 600. So we find that D equals 600. That means you have to remove 600 trout fish every year. And it does make complete sense. So how is that? So if you start with 6,000, by the end of year, it will increase by 10%. So it would become 6,600. How much is excess? Well, this is 6,000. That is the initial plus 600. Now, if you take out 600 from that, you are left with 6,000 again. And this process will keep continuing. You start with 6,000. There is a reproductive process that increases it by 1.1. Sorry, it increases by 10%. So the multiplication factor is 1.1. You get 6,600. But then you again remove 600 of trout fish, maybe the older ones. You get back 6,000. So this loop will keep continuing as the year passes by. So this brings to the last part of question number 1, which is a mathematical induction problem. So to model predicted number of trouts, the lake owner has been using sequences generated by this recurrence relation that we started with. Un plus 1 equals a factor times un, which turns out to be more than 1 minus d. So here it specifies that r is not equal to 1 and they are both positive real numbers, r and d. So use mathematical induction to prove that un can be written in terms of the initial value of u, which is u1, and r and n and d. So basically, this is like a closed form equation as a function of n, where you do not have to, as opposed to the recurrence relation that is given initially. So we have been using closed form expression for Tn's and Dn's and Cn's. Here we will have to prove it. So let's go ahead. So the proposition, so this is the recurrence relation. Let us call this, and we have this proposition that we have to prove? Un equals u1 r to the power n minus 1. Let's call this equation P. P like P for proposition. So start with n equals 1 in R. So you get u2 n plus 1 u2 plus R times u1 minus d. Now let's put n equals 2 in the proposition equation. So we get u2 equals u1 into r to the power 2 minus 1 minus d times r to the power 2 minus 1 minus 1 divided by r minus 1. So r to the power 2 minus 1 is nothing but r, because the exponent becomes 1. So this is nothing but u1 times r. And if this is r minus 1, this factor on the second term, so the numerator and denominator will be equal to each other and cancel. That's how we get u1 times r minus d. So we do observe that the proposition gives us the same answer as the recurrence relation. So we can say that P2, the proposition, is true, or proposition true holds. Proposition at n equals 2 holds. So what you're gonna do is that, as the rule of the mathematical induction suggests, we say that assume Em holds. That is, in this case, can indeed be expressed in this form, closed form that has been suggested. Now we have to see if Pm plus 1 holds as well. So what is plus 1? So we start by using the recurrence relation here. We know for sure. We know the value of to be true, like here. We'll use this structure of and the recurrence relation we have, which is r times minus d for plus 1. So I multiply the entire thing by a factor of r. And finally subtract d. So we get r to the power n. So here I'll just collect all the terms first. R to the power m minus r. Now this r divided by r minus 1 minus 1 will give us plus r minus 1, this factor, from this term actually. So this r and r will cancel. So the right hand, the second term will become d times r to the power m minus 1 divided by r minus 1. Now m plus 1 minus 1 is basically m. So r to the power m can be written like m plus 1 minus 1. Similarly here as well. So the expression we finally end up getting is indeed in the form of, you can just explicitly write it or just deduce it from the expression. It's m plus 1 minus 1 minus d times r to the power m plus 1 minus 1 minus 1 divided by r minus 1. So p of m plus 1 holds as well. So P2 holds, Pm holds, implies Pm plus 1 holds. These two together says that Pn holds. So that's the proof. So in the second question, we'll have to explore palindromic polynomials and its certain properties. So it would be quite fun. A polynomial is said to be palindromic if the sequence of its coefficients remains the same in reverse. So let us consider this example. This polynomial, if you write in the order of decreasing power of x or exponent of x, x square x1, its coefficients are 2, -5, 2. If you take the sequence in reverse, it will still be 2, -5, 2. Similarly, this is 1, 4, 1, back and forth is same. X square plus 1, it has the coefficient of x is 0, so we can write it as 1, 0, 1, 0 being the coefficient of x. So this polynomial is also palindromic, and hence this definition that the sequence of its coefficients remains the same in reverse. This question asks you to investigate some properties and solutions of palindromic polynomial equations. In parts A and B, consider quadratic equations of this form ax square plus bx plus a equals 0, where a is not equal 0. So notice that ax square plus bx plus a, this polynomial is palindromic because the sequence of coefficients is ABA, and reverse it's also ABA. So there is another property that has been mentioned, that this quadratic equation that we saw as an example, 2x square minus 5x plus 2. So this is a palindromic polynomial, and its roots, when it's put into an equation form, homogeneous equation form, its roots are 2.5. These roots form a reciprocal pair. Why reciprocal pair? Because once you multiply these two roots values, it becomes 1, or one root is reciprocal of the other one. That's why they are called reciprocal pair. So the first question asks, determine the roots of x square plus 4x plus 1 equals 0. Give these roots in the form s plus or minus square root t, where s is an integer and t is a positive integer. So if you like, because we can take square root of a positive integer, that would be a real number. So we'll have real roots. So we can solve this quadratic equation by completing square. So if I just write this polynomial, let's say this is p of x. We complete this square. We write 4x as 2 into x into 2. We complete the square by adding 2 square and then again subtracting 2 square plus 1. So we end up getting the first three terms will give us x plus 2 whole square. And this is -3. So now px equals 0 means x plus 2 whole square minus 3 equals 0. And hence we get x equals -2 plus or minus square root 3. So this is like s equals -2 and t equals 3. and the form is s plus minus square root t. These are the roots. Hence or otherwise, show that these roots form a reciprocal pair. To show that, we just have to multiply the two different roots and show that it's one. That's the definition of reciprocal pair. So -2 plus root 3 and -2 minus root 3. So they are in a plus b into a minus b form, where a equals -2 and b equals square root 3. So this is a plus b, a minus b becomes a squared minus b squared, which will translate to -2 squared minus square root 3 squared. And this is nothing but 4 minus 3, which is 1. So we have shown that the roots are form a reciprocal pair. So we showed one example where this is a palindromic polynomial and its equation has reciprocal pair of roots. So we show another example. So show that the complex roots of x squared plus 1 equals 0 is also a reciprocal pair. So x squared plus 1 equals 0. So let us assume that the two roots are alpha and beta. So I can write x squared plus 1 as x minus alpha and x minus beta equals 0 because these are the two roots. So these two equations are equivalent. So if they are equivalent indeed, then we can expand the left-hand side of this root form equation to have x squared minus alpha plus beta into x plus alpha beta equals 0. So now we can compare the coefficients of each power of x. So alpha plus beta equals 0 because in the original equation, there is no coefficient of x or x coefficient is 0. Here the x coefficient is alpha plus beta. So alpha plus beta must be equal to 0 because these two are equivalent equations. And by the same logic, alpha beta is equal to 1. Well, that's the proof because we assume that alpha and beta are the two roots and hence it can be written as x minus alpha and x minus beta. And if we compare that these two polynomials are same, we showed that alpha times beta has to be equal to 1. So this proves alpha and beta forms reciprocal pair. All we had to show is their product is 1. In the following question, it asks let p of x be any generic form like x squared plus bx plus a, where a is not equal to 0. Then verify that this expression holds when x is not equal to 0. Okay, so we have to verify that p of x is same as x squared times p of 1 minus x when x is not equal to 0 and p of x equals ax squared plus bx plus a. So px equals this already given. So let's start with the RHS, the right hand side of the proposition that you have to prove. So that is x squared times p of 1 over x. So x squared is a factor, so we take this out. What is p of 1 over x? It's just putting 1 over x in the place of x in the polynomial expression of p of x. So 1 over x squared. So a Let me just write it clearly here. Instead of a of x squared, we will write a times 1 over x squared plus b times 1 over x plus a. Now, the remaining task is to put this x square back in the square bracket. So the external factor x square, let's like multiply by that fact inside. So here we will have the first term will be a x square times 1 over x square. They'll just cancel each other. Bx square times 1 over x, 1 power of x will cancel, plus ax square. So the first term is a, the second term is bx, and the third term is ax square. So this is really p of x written in a reverse order. So this is nothing but p of x. If you just rearrange these terms to write it as ax square plus bx plus a, this is nothing but px. So this is the left-hand side. So the question 2 continues here. Here in parts D and D, you may assume the result that a polynomial of degree m is palindromic if and only if p of x equals x to the n p of 1 over x. So like we proved that if p of x is a palindromic of degree 2, then we showed that x squared times p of 1 over x equals p of x previously in the previous part. Here it is generalized for degree n. More precisely, if p of x is equal to x to the n times p of 1 over x, this is true if and only if, so this is a two-way condition, p of x is palindromic. So this is something we can assume for part B and D. So the first part or the part D says that if this is true, so that if alpha not equal to 0 is a root of px equals 0, so alpha is a root of p of x equal to 0, such that alpha is not equal to 0, then 1 over alpha is also a root. So p of alpha is equal to 0. We can argue that since alpha is not equal to 0, since alpha is not equal to 0, p of alpha equals alpha to the n, p of 1 over alpha. Well, that is given, like use this equation. Hence, p of 1 over alpha. If we take alpha to the n to the other side, we have to divide by alpha to the power n, and that is fine because alpha is not equal to 0. So we are not dividing by 0. So we can divide by something that is non-zero. But we know that p of alpha is 0, so this becomes 0. So we end up getting p of 1 over alpha equal to 0. So 1 of our alpha, 1 over alpha is indeed another root of p of x. All right, that was fairly easy. Let next part, let f of x equals p of x into q of x. So p of x is a polynomial, q of x is a polynomial, and in fact, both of them are palindromic polynomials of degree n and m respectively. So p of x has degree n and q of x has degree m. So that f is also a palindromic polynomial. So f of x, which is p of x and times q of x. So first of all, its degree is x to the n plus m. So how do we show that this is a palindromic polynomial? So we can use this proposition that if we can show that f of x is equal to x to the n plus m, that is the degree of the polynomial f of x times f of 1 over x, then f of x is palindromic. So how do we show the left-hand side? So we are given that p of x and q of x are palindromic, which means p of x is equal to x to the n p of 1 over x, and q of x is equal to x to the m into q of 1 over x. Why? Because p and q are palindromic, and this proposition that we started with is two-way, like if and only if. So p of x is palindromic means that this equation holds. Q of x is being palindromic means also this equation holds. So you can combine these two. You just can multiply p of x into q of x, which will give me x to the power n plus m and p of 1 over x into q of 1 over x. And it's very easy to notice that the left-hand side is nothing but f of x, and the right-hand side is nothing but x to the n plus m into f of 1 over x. So that proves this proposition that f of x equals x to the n plus m f of 1 over x. So that is indeed proving f of x is palindromic. So here we had to use this proposition if and only if both ways. So this was an interesting proof. Now it says, consider the palindromic polynomial this x to the power 4 plus 2x square minus x square plus 2x plus 1. This polynomial can be expressed in this form. So now we are expressing like f of x in p of x and q of x form, where both p of x and q of x are palindromic. So notice that for if this is p of x, then its sequence of coefficients are 1, mu 1. So this is palindromic. This one, the second factor has coefficients 1, mu 1. This is also palindromic. And f of x has 1, 2, minus 1, 2, 1. So f of x being product of two palindromic polynomials by itself is again palindromic because this sequence is also palindromic, this sequence. By forming and solving an appropriate system of equations in u and v, determine the value of u and the value of v. So that is part f. So what we are asked to do, that if I can express f of x in terms of these two polynomials as a product of these two polynomials, more specifically, if I can express x to the 4 plus 2x cubed minus x squared plus 2x plus 1 as 1, so this is 1 plus ux plus 1, 1 plus vx plus 1. If we expand these two factors, we will get 1 plus u plus v times x cube plus uvx squared plus u plus vx plus x to the power 4. So now we can compare the coefficient of each power of x on both sides. So here we get u plus v equals, so if we compare the coefficient of x cube or x, it doesn't matter, both of them have same coefficients. U plus v equals 2, and uv, that is the coefficient of x squared, is -1. So here we can substitute v equals 2 minus u. If we substitute that in the second equation, we get u 2 minus u equals -1. So u squared minus 2u. So we have missed a term here. This coefficient of x squared is not uv times x squared. It's actually uv times plus 2x squared. Hence, this equation changes to uv plus 2 equals -1, or uv equals -3. So we get u square minus 2u minus 3 equals 0. The middle term can be written in terms of the factors as -3u plus u minus 3. And we have u minus 3 times u plus 1 equal to 0. So the two roots of u is 3 or -1, and correspondingly the values of v would be -1 and 3. So basically at the bottom line is f of x can be expressed as 1 plus 3x plus 1 times 1 minus x square plus 3x plus 1, x square minus x plus 1. So product of these two polynomials. So either u equals 3, v equals 1. So the two possible solutions are 3 minus 1 or -1. 3, they are basically same. The product would be same. Doesn't matter in what order the polynomials are being multiplied. So the next part is asking, hence find all the exact complex and purely real roots of x to the power 4 plus 2x cubed minus x squared plus 2x plus 1, or in other words, find the roots of f of x. So we can separately find the roots of the two polynomials that gives rise to, so these two polynomials that gives rise to f of x by product, taking a product. So let's do that. The two equations are x squared plus 3x plus 1 equals 0, and x squared minus x plus 1 equal to 0. So the first equation, if we complete the squares like before, the square term becomes x plus 3 by 2 whole square minus 9 over 4 plus 1 equals 0. So x plus 3 by 2 whole squared equals 5 by 4. And x equals -3 by 2 plus or minus square root 5 by 2. Here also you can complete the square. The square term becomes x minus half whole squared plus minus 1 over 4 plus 1 equals 0. X minus half whole squared equals negative 3 by 4. So these roots will be complex because we have to take square root of negative 3, which is square root 3 times iota for I. X equals half plus or minus square root 3 over 2I. So the four roots are just the four roots. So the real roots are, these are purely real roots. And the complex roots are half plus minus square root 3 by 2I. So this brings to the last part of question number 2. So consider this palindromic polynomial equation, which is of nth degree, and where n is odd. We have to show that minus 1 is always a root of this equation. So we can use mathematical induction principle to prove this question. So how do we do it? So let's first assume the smallest odd number we know, that is n equals 1. In this case, the polynomial would be x to the n, which is x, plus there are no middle terms, just x plus 1 equals 0. So x to the n minus 1 is nothing but 0, like x to the 0. So that is just the one term, but the one term cannot have any non-one coefficient. So it has to be just x plus 1. So according to mathematical induction, we assume that for n equals m, we have p m of x, where if m is odd, we have pm of x, and pm of x equals minus 1 is equal to 0. That means that minus 1 is a root of pn, or the nth order polynomial. So let us say this is true. So I assume this. Now can we show that for n equals m plus 2, which is the next odd number, this is true again. So pm plus 2 also has a root minus 1. So let's write pm plus 2. This is x to the m plus 2. Let's say 1x to the m plus 1. So the one trick here is to observe that starting from the second term to the last second last term, if we take x common and a1 common, so let me just write it first. We take a1 times x common factor, we get x to the m plus a2 divided by a1 x to the m minus 1 plus da, 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 a2 by a1 x plus 1. And the last plus 1. So if we take a1x as a common factor, we do get a polynomial of degree m, where m is odd, and it is indeed a palindromic polynomial. This is because all the middle terms form a palindromic sequence. Starting from a1 to a1 is also a palindromic sequence. So it must be that the sequence starting from 1 to 1 is a palindromic sequence if we take a1 common. And we take another factor of x common along with a1, so that this becomes a polynomial of nth degree, and minus 1 is a solution. for such a polynomial. So this and the remaining terms, which is, so you can just collect x to the power m plus 2, which is an odd exponent of 1 plus 1 at one hand, and we can just write this is some pm of x times a1x. So indeed, if we now put x equals -1, this would be -1 plus +1. Because this is an odd power of -1, so that would be -1 plus pm of -1. Now, any palindromic polynomial of degree m, which is an odd degree, will be 0 times a1 times -1. So this is 0 by the previous assumption. This guy is also 0. So if you just add those two, pm plus 2 is also 0 at x equals -1. So this is pm plus 2 at x equals -1. So we do show that pm of -1 equals 0 implies pm plus 2 at -1 is also equal to 0. So hence, for all n odd, pn, like the palindromic polynomials, evaluated at -1 is 0. So -1 must be root of all such palindromic odd degree polynomials.